Hi, welcome back to the tutorial on deep learning. So here, last time we saw what is deep learning, how we can basically get started with deep learning. We saw the basic mathematical model proposed by McCullough-Pitts of the neuron. We saw the Rosenblatt's perceptron, which is basically the new age perceptron that is being used in the feed-forward or the other deep learning architectures that we see today. We also got a brief overview of how this perceptron learns. In today's class, we'll dive deep into this learning algorithm. We will also see the feed-forward network, that is, the way a single perceptron or multiple perceptrons can be combined together to learn different and complex patterns that may be present in the data. So let us get started. So first we'll look into what is a feed-forward network. So we humans in our brain, we have hundreds and thousands of neurons, with each neuron performing some specific function. For instance, here, if we are to identify an object that we are seeing, so we want to identify whether the object is, say, whether it is a person, whether it is a cat, or whether it is something entirely else. We look at the object through our eyes, which basically acts as the stimuli, which activates some neurons in our brain, which then activates further different neurons in our brain. And with a combination of all these, with the neurons, all the different neurons, which are basically passing the information in a hierarchical fashion, we are able to make a judgment, we are able to make a decision about the object that is in front of us. So here you can see that the object is being looked at by the eye, and it is passed on, the stimulus is passed on to the first neuron here, which is then further passed on to the next neuron based on some kind of activation that it does. Then it is passed on to another, followed by another, and so on. Then now each of this neuron in this whole pathway or this whole complex structure performs a specific different task. So for instance, it might be that the first few neurons, first few levels of neurons, they are just identifying some sort of shapes in the object that we are seeing. That is, where does the edges of the object lie? How many circles are there in the object? Where does the circles lie? Right? So the first few preliminary neurons, first few levels of neurons, they are just considering these basic informations of finding edges and say the contours and the basic things, the total basic structure of the object in front of us. Then the next few layer of neurons might be associating these objects to, say, a larger object. For example, say we see a structure like this. This is being identified by the first few layers of the neurons, and the next few layers associate this structure with, say, a nose, if it is a person in front of us. So the next few neurons, it basically does a complex task of querying through our knowledge of what this structure might resembles to, and then associate the structure to a already known, already seen object from our past. So the first few neurons, as mentioned, identify just the edges and the boundaries of the structure. Then the next might be able to associate the structures to different objects. And finally, the last few neurons, the higher level neurons, which associate these smaller objects into a bigger image and can help us to identify whether these the combination of these structures make up a face or not, and what kind of face does it make? Is it an animal's face or a human's face? Now all of this is working in a hierarchical fashion. That is, we have some, so here for instance we might have some neurons here which identify the edges, and the information of these neurons, they are passed on to the next neurons which identifies, say, the different structures of nose, mouth and eyes, and these are further passed on to the next level of neurons which identifies whether it is a face or not, and then lastly it identifies of what kind of face is it. Now this is something that we do on a daily basis without even realizing it, but in order to mimic this behavior in computer machines, we are proposing to use the basic perceptron in an hierarchical fashion. So here we have this perceptron here, which is a single unit which takes the input that we just mentioned as a real numbers. It has some weights associated with each of these inputs, and it performs some kind of aggregation over these inputs to give us an output which basically says if we want to activate this perceptron or not. Now we might use multiple of such perceptrons. So say this perceptron, let's call it P. We might use multiple of such perceptrons in our network, and each of this perceptron is responsible for identifying different things. For instance, we might say that these first few perceptrons, they are to identify just the edges of the image that we are seeing. Then this hidden layer, it is responsible for associating these edges to objects, that is, whether it is a nose or a mouth or an ear and such that. Then finally, this output layer, it is responsible for determining whether these objects together constitutes a face or not. And then finally, these outputs are given out to the environment, and we make a decision based on the outputs that we receive here. So if we are to employ the perceptron in such a way, so basically this structure where we use multiple perceptrons in a hierarchical fashion, this is known as a feed-forward network or multi-layer perceptrons. So as the name suggests, there are multiple layers of the perceptron architecture. So these are known as multi-layer perceptrons or a feed-forward network, since we are feeding the input in the forward fashion and there is no feedback that is involved here, right? So feed-forward network or the multi-layer perceptrons. Now, as we saw before, just like in our brains, first few neurons, first few stimulus of our brain, they are responsible to identify the visuals that we are seeing, the colors that we are seeing might be. Then the first hidden state, they are just identifying the edges in the image that we are seeing. The second hidden state is identifying the corners and the contours, so that we are able to differentiate the different objects in the image, that how many objects are there and how they are different to each other. Then the third layer, it basically is associating these different edges and contours into constituting an object from this layer. And so as we saw here, the first layer identifies the edges, and then we are associating these edges into making these objects such as nose, mouth and eyes. So this is what is happening here in the third layer. And then finally, we identify the object in the final layers of our architecture, where we can identify whether the structure is a car, it's a person or an animal, right? So yeah, so this is how a feed-forward network works. And why do we need it? Because a single perceptron or a single neuron might not be able to capture all the nitty-gritties of the task that we want to achieve. So for here, we want to achieve the task of object identification. So a single perceptron might not be able to capture all the different kinds of attributes that we want to consider in order to identify the object. Whereas if we employ various neurons across different layers, we might able to capture this object identity in a better fashion, as multiple neurons across multiple layers will be capturing different attributes, different properties of the image that we are seeing, and then must be learning different associations between these objects of the image in order to generate the better output for object identity. Now we have seen what is a feed-forward network. Now in this feed-forward network, as we have seen before, that each perceptron, it is associated with some kinds of weights and bias, and based on these weights and bias, it gives us an output. Correct? But now, if we are to learn, if we are to modify these weights and bias in a way so that the predicted output of our neuron, the predicted output of our whole architecture is the output that we want, is the desired output, then we must learn these weights and bias in a way that whatever computation that is happening in this network gives us an output that is closest to the desired output. So it can be this whole learning process, it can be achieved through a process known as backpropagation. So as the name suggests, backpropagation means propagating the error that we achieve at the output layer of the network to the throughout the network till the input layer. Since we are backpropagating this error, and based on this error we are modifying the values in a backward fashion, this whole process, it's called as backpropagation. So this is basically an algorithm which is used to train a neural network, and the method that it uses to identify the amount of change that we want in the weights and the bias of our network, that method is called as chain rule. We'll see this right now. So the first process before backpropagation, it is to definitely do a forward pass through the network. That is, firstly, we initialize these weights and bias in a fashion, there are multiple ways for initializing these weights and bias. One of them can be to just do random initialization. That is, we randomly set the bias and weights for the initial level and just perform a forward pass in the network. So we'll just look at what a forward pass is. But before we do that, let us take an instance of this. Let us suppose that we have this kind of a feed-forward network with us. So basically it has 4 layers. This is the input layer, right? Then we have the first hidden layer here. Right here it is actually written. We have this is the input layer. Then we have the first hidden layer here. Then we have another hidden layer here, and which is followed by the output layer. So we basically have 2 hidden layers, an input layer and an output layer in our network. The input layer, it takes the input from, it takes the real valued inputs from whatever source that we have. Then this hidden layer, it calculates the weighted aggregated sum of the inputs that we receive here. So basically this line that you can see here, this line, it is this edge is basically associated with the weight that we want to give to this input. So we can call it W11, and since it is of the first layer, then there will be a superscript of 1 here. This is just like the norm in which the weights and the biases and the other values of the network are written. Then we have this another edge associated with this first input neuron, which basically tells us how much weight do we have to give to this neuron for the second neuron of the first hidden layer. So this weight can be written as W12 say 2 1, that is for the second neuron of the hidden layer, and the weight is associated with the first input. And again, since this is the first layer, then a superscript of 1, right? Then this particular weight, it can be written as W 1 2 and 1. That is it is associated with the first neuron of the first hidden layer and the second input, right? So based on these values, and similarly this will be W13 and this will be W14 of the first layer, right? Now we have this input layer which contains A11, A12, A31 and A41, which together can be written as A superscript 1, that is all the values of A present in the first layer. Then we have all these weights for the between the first layer and the first hidden layer, which can be represented as W superscript 1. Then we have these resultant values for Z, the resultant value for the that is the weighted aggregate. So here, if we just look at this first Z here, so Z1 of the second layer, it is basically the weighted sum. So it is like if we multiply W11 of the first layer with A1 of the first layer plus W12 of the first layer into A2 of the first layer plus W13 of the first layer into A3 of the first layer, and finally W14 of the first layer into A4 of the first layer, right? This gives us the value of Z1 of the second layer. Now, based on this value, since this is a real number, this is a real number, all of these are real numbers, we would get a real number for this Z1. But now, since it's a perceptron, we might want the value for the output value for this perceptron to be a Boolean variable. So we have multiple activation functions, something that is called as activation functions, which basically modifies, which is basically a transformation of this aggregated sum into an activated value. So there is so we will not go into the depth of the activation function, but the only thing that is important here to know is that it is basically a transformation, a nonlinear transformation from the input, whatever comes to this activation function, to the output, right? So this A value that we are getting, this A1 for the second layer, it's basically after we are passing this Z value through an activation function, right? So there is one activation function known as sigmoid, which like if we have to calculate the sigmoid for f x, then it will be something, the graph of the value would be something like this. That is, for the 0th value we'll be getting some negative values, and for the positive values, for the 1 values, we're getting some positive values, right? So this is just one kind of activation function. But other than that, we have many different activation functions, and this is how we basically get the value for A. That is, we pass the aggregated sum value, the weighted sum, through an activation function. So this is how we get the value of A. Now, if you we see that how do we get A, how do we get Z? Now, for the whole hidden layer 2, we can write it without this subscript, because the superscript basically represents the layer. So for the whole hidden layer 2, we can write that Z of hidden layer 2 is actually equal to the W, the weights associated with the hidden layer 1, into this A's that are associated with the hidden layer 1, plus, now this hidden layer, basically there is a bias here, which we need to add to this so that we can compare the whole aggregated sum with whether either it is greater than 0 or not, right? So plus b of the first layer. Now if this z2 and then again this a1, a2 here will be the function, will be the value of this z2 after it is passed through an activation function, right? So now we see that this is how we get the z2 and the a2, right? So and similarly with the same approach we can get the values for z22, then for the second hidden layer also we can get the value like this. So for the second hidden layer it will be like we'll have, so let's write it down here. We'll have for the this second hidden layer we'll have z of 3 equal to the w2 that we have here, the weights associated with layer 2 into this ai's value that we are getting, since this is the input for our second layer. So we can write them down as a of superscript 2 since it is associated with the second layer, then w weights of the second layer multiplied by the activation of the second layer, and then plus the bias of the second layer. And finally this a3 that we have is the activation function applied to the z value for the layer 3, right? So we just see the equations here. We have the input layer, that is x, that is the first a's that we have, which is equal to the x. Then we have the hidden layer 1. For the hidden layer 1 we have an equation like as we just saw previously, z2 is equal to the weights associated with the between the weights associated between the first layer and the first hidden layer multiplied by the input plus the bias. And then we have the activation function that is applied to the hidden layer 1, and similarly we have the z at hidden layer 2 and the activated value for the hidden layer 2. Now finally at the output layer we have s, which is equal to the weights associated with the weighted sum of the values that we are getting at the last hidden layer and the corresponding weights, right? So the final s is w3, that is the weights for hidden layer 3 for the total layer, like the third layer, and the activated value of the third layer, right? Then now this s that we have, the output that we are getting here, it is not necessary that this output is the same as the desired output that we want. So for instance, suppose we are to perform a task of sentiment analysis as we discussed in the last class. So for the task of sentiment analysis, there are basically two classes with us. That is positive sentiment and a negative sentiment. So for instance, 0 represents the negative sentiments and 1 represents the positive sentiments. Now these are basically the value that y can take, and we have some input x with us. So now for instance, for a particular x, ry is so let us create this table in a different fashion. Suppose we are given this x and y as our desired data, and for a particular value for x's, the ground truth label of y, that is the actual sentiment associated with this x, is basically positive 1. However, our model, whatever model that we have with say random initialization of weights, it is suggesting that this input x is actually belonging to a negative sentiment, which is not true in this case, which is basically a wrong prediction. So we want to modify a network in such a way so that the model is able to learn that it is predicting it wrongly, and it modifies its weight and biases such that for the future prediction it becomes correct, right? So in order to do that, the first thing that we need to identify is whether it is predicting it correctly or not. So to check whether it is predicting correctly and to check how wrong our network is performing, there is something that is called as a cost function. Right, now again, we'll be not going into the depth of different kinds of cost functions that are present, but there are, just like an activation function, there are different cost functions that are present in the whole deep learning paradigm. So here we'll just learn about the intuition behind this cost function. So basically this cost function, it is calculating how the predicted output S is different from the desired output Y. So for instance, here a cost function can simply be the difference between the predicted value and the desired value. So here for the case of sentiment analysis, cost function can be simply like yi bar minus yi, where yi bar is the, suppose this is the ith label, right? So yi bar is the predicted value of y that we're getting, which is either 0 or 1, and yi is the ground truth value that we have. So for example, if the predicted value is 0 and the ground truth is 1, so here the cost would be 0 minus 1 equal to minus 1. Now we know that there is something called cost, and we know that we can gauge the difference or basically the issues that our model has in order to identify the correct output. So now we want to use this cost. We want to use this particular value in order to modify the weights and bias so that this cost is minimized. That is, this difference between the predicted value and the actual value is the least, it is minimized, the least that we want, right? So now to do that, we'll calculate the derivatives. Now why the derivatives? Because so we know like what a derivative is. So suppose we are to calculate the derivative of y with respect to x, then what does this derivative signify? It signifies that with the change in the value of x, how does the value of y change? Correct? So we want to see that with how much change in the value of weights, right? How does this value of cost change, right? So if we are to change this value of weights towards a particular direction, how will the value of cost change in such a scenario? In which direction will it go? Will it increase or decrease? So based on the derivative, we know that we want to minimize this cost. So that is why we will, based on the change that we observe here, based on the value that we observe here, that how much the C will change based on weights, we will take this C in a direction such that it is minimized. Now in order to see how much the weights change, we need to calculate this derivative. Correct? Now how to do that, right? So this is done by something called as chain rule. Now we have the cost here, the C here, that is the cost between the predicted value and the actual value. Then we need to see how does the weights and biases are affected by this C. So that is, we need to calculate the change in C based on the change in weight. Now this can be done by using chain rule. That is, we calculate this derivative of C based on, say, the Z values that we have, and then the change in the Z value based on the weights. Since we see here that this weights here, they are not directly interacting with the cost C or the output S, rather they are interacting with the Z, and this Z is further with A and this A further with S. So we kind of move backwards one step at a time. We see that how is this S affected by this Z? Sorry. How is this S affected by this Z, and further how is this Z affected by the weights? So to do that, to calculate the amount of change in the cost with respect to the weights, we first calculate the amount of change in this cost with respect to the Z and the amount of change in Z with respect to the weights. So this is basically the chain rule. And if we'll need to move more backwards, we'll do that. We'll just see further. Now here we know that this Z is given by the equation of the summation of all the W's, the weighted sum, right? The W's multiplied by the weights plus the bias, right? So in this particular representation that I'm writing, I'm just skipping the subscripts and the superscripts so that it becomes easier to understand here, and then we can add the superscripts and subscripts based on the layer and the value for the Z that we are working on, right? So it is more like a generalized form. Now since we know that this is what Z is, we can calculate this derivative, right? So the change in Z with respect to W, we can calculate this derivative, and we see that it is basically A, right? The derivative based on this formula and with respect to W is A. So we replace this value here, and we see that the change in C with respect to W can be given as the change in C with respect to Z multiplied by the A. Correct? So now this is basically the change in the cost function based on the particular weights. Now similarly, based on this Z value, I'm not erasing that Z value right now. So this we calculated for the weights. Now we also want to modify the bias in order to minimize the cost function. So we also need to calculate change of cost function with respect to the bias. So it can again be used by the chain rule, that is the change in cost with respect to Z and the change in Z with respect to the bias. Now this value based on the value of the equation of Z that we have, it can be calculated. So derivative of Z with respect to B would be basically 1, right? So we replace this value here, and we see that derivative of C with respect to the bias is actually the derivative of C with respect to Z into 1. Correct? Now we just add, this is more like in a general fashion, we add the superscripts and the subscripts here to just identify that for each layer and for each of the pair of weights, this is how we can calculate the change of the cost with respect to the weights and the bias. So the next is basically the bias that the bias, that is how it is affecting. And finally, what we do is that based on this change, based on this derivative, based on the direction of the change, we modify our weights for the next iteration. So we modify our weights in such a way that we multiply this derivative, this change that we want in the weights value, with a learning rate here. So this learning rate is something which regulates that at a particular iteration, how much, like what would be the amount that we want this weights and bias to be modified. So this learning rate is basically something that helps us to regulate the convergence of the solution. That is, we can say that the solution has converged when the change in the weights and bias between two iterations is below a threshold. That is, we can say that the weights and bias in between the two iterations are more or less similar. So that is when it can be one of the criteria for convergence. So that is when we can say that the model is converged, and this learning rate helps us to regulate the rate of that convergence. So it is essential to set this learning rate to a correct value, since a higher learning rate or a lower learning rate from the optimal value can result in haywire learning. So again, not going into the detail of it, not going into the depth, since it is more like an overview of all the different architectures and the structure of deep learning. So not going into the detail of learning rate, but yeah, it is something which regulates the amount and the extent of convergence in our model. Then, so this is an example of the forward pass. Here we have the cost here is just like the cost between the S and the actual Y. Now we want to calculate the how to change this value of W2 to this weights based on the X based on this cost. So we calculate the derivative of this cost based on these weights, and in order to do that we apply the chain rule. We have this cost, and we see here we move backwards here. So we see that first this this cost is interacting with A2. So we just and this A2 is basically coming from Z2. So we have this derivative of cost with Z2 and then Z2 with W22, correct? Since this Z2 is directly interacting with W22. So we have this value of Z2 with W22. Then we have this, now again this whole thing can be written in the with the help of this A2, since we see that cost is the one directly interacting with A2. So we again apply chain rule here and write this particular thing like this, that the derivative of C with respect to A2 multiplied with the derivative of A2 with respect to Z2, and as we saw before, this value that is Z with respect to weight, we saw this here, that is derivative with respect to weight is basically this value, that is A, derivative multiplied by A. So we have this here, the derivative multiplied by A. Then again, to calculate the derivative of this, so what is A2? A23 is basically the activation function applied on Z23, and the derivative of this would be the derivative of this function. So we have this F's derivative here, and the normal cost of the derivative of cost with respect to A2, right? So this is how the backward pass takes place, and based on this particular small algorithm, we modify the weights and biases with respect to these derivatives in order to get in order to achieve convergence and to get the optimal value for these weights and biases. Now today we saw a feed-forward neural network, and we saw the major algorithm that is being used to optimize these neural networks so that learning actually happens and we get the optimal value for these weights and biases, so that we get better accuracy, better performance for our models. Now in the next class we'll see different architectures other than this feed-forward network, for example convolutional neural networks and recurrent neural networks, and then we'll look into something called attention as well. So thank you.